friends, it's Mr. G here today to talk to you about a really cool property of waves that we actually have a chance to experience every day, and that's this idea of interference. I'll start off with a classic demonstration that some of you I'm sure have seen before. It's this idea of crystal glass in front of a speaker emitting whichever frequency we're looking for, and if we hit just the right frequency, well, watch what happens. And so the question you guys might be asking yourselves is, what the heck's going on? How do we deal with that? And to start by talking about that, we have to talk about this idea of two waves in the same medium. So you'll notice that we have sound going from air and then it gets into the glass. And what happens here is that each of the waves that go in affect the medium independently. And if we want to find out what the overall effect of these waves have on the medium, we have to talk about this idea of superposition. So by definition, superposition is the total amplitude of a wave is actually equal to the sum of the amplitudes of the individual waves. So isn't that cool? If we keep bombarding an object or a medium with certain kinds of waves, we're going to end up with an overall effect, which is just the sum of their amplitudes. So if we take a look at the first type of interference, if we have two waves with the same frequency and phase, well, we get this idea of something called constructive interference. So you can see that these look essentially identical because they are in this case. And all you do in this case with constructive interference, I know it sounds like an oxymoron, but you just add up all of the amplitudes and you get a wave that is, in that case, double the amplitude of what it was originally. And we have here a nice little demo to show that effect. You'll see here they're using a mechanical spring to show that there's two waves going up, and watch this, bam, look at that huge wavefront now. Instead of one individual wave, in fact it is, or sorry, instead of two individual waves, it is in fact one very large individual wave. And of course it's going to slow down after the fact because, hey, it's just a mechanical wave. The second type that we would look at is if two waves have the same frequency and opposite phase. So remember, phase in this case refers to the idea of whether the waves line up or not. And so if we take a look here, you'll notice that the troughs of one wave line up with the crests of the other waves. And when that's the case, well, boy, they sure look like mirror images of each other. When they run into each other, what's going to happen is they are going to cancel each other out, and that's this idea of destructive interference. So the easiest way to remember destructive interference is the idea that we're just going to subtract the two amplitudes. And again, same spring demonstration. Instead of the waves going on the same side, they're going on different sides, and if you look, they run into each other, they do this little dance. Now it doesn't look like two wave fronts, it kind of looks like a bit of a swervy line, and inevitably it ends up being a flat line because the two wave fronts actually perform destructive interference. So a great place to see both constructive and destructive interference taking place are in bubbles. If you take a look at the colors are the result of light coming through air into the soap. Now, because soap isn't 100% reflective, it's going to reflect a certain portion of light, but it's also going to let a certain portion of light come into the medium and then bounce back. And when that occurs, the interaction between the wavefront that's coming out of the soap and the wavefront that's coming from the reflection in the air results in these different colors that you see. If you look at the clear portions of soap bubbles, that's actually a demonstration of destructive interference because all of a sudden they are back in phase, and when, as I said before, waves are in phase, the result is going to be destructive interference. So something we really want to look at when we're talking about stuff like this is this idea of a standing wave, and this picture here is a great demonstration of that. You'll notice that we have some different properties of standing waves. You can see an amplitude, you can see these little scrunch down sections in the middle, kind of here and here, and those are those ideas of nodes. Well, the opposite of node is antinode, so if we're not dealing with the spots where there's essentially no amplitude, we're dealing with the spots where there's lots of amplitude, and in this case, these here are the antinodes. So if we take a look, standing waves are caused by a bunch of different ideas, but inevitably come down to the idea of constructive and destructive interference. when we have absolutely no amplitude, this is obviously a place where destructive interference has taken place, and these are what we call the nodes. And then, as I said before, the complete opposite, when we have the largest possible amplitude, which we saw from our picture, those are in fact called the antinodes. So if we take a look, here's a nice little GIF for you to sort of show. Here's a wave that's vibrating, and you'll notice that even though when it is flat, that's just a transition, because don't forget, a wave is going up and down. Just because a wave goes flat doesn't necessarily mean that's destructive interference. But at the same time, you'll notice that the spot right here never moves up or down, because it's nothing but destructive interference, as is the case here and here and here and here. However, if you take a look at this wavefront, you'll notice that there's amplitude and there's amplitude again. So now we're dealing with the antinodes, and the same thing on the other side. So this is a typical vibrating standing wave. Now, take a look at this. If we have a fixed end to a wave, so imagine that spring is attached to a wall, or in this case we have a demonstration with some wood blocks that actually have a fixed end to the right. It will reflect and invert its amplitude. This is a crazy experience, but check this out. The wavefront is moving forward towards the fixed point. Once it hits the fixed point, watch the wood. Goes right underneath and inverts itself. So when a wave reflects off something, as I said before, like a wall, or maybe a medium, what's going to happen is that amplitude is going to invert. So when we're dealing with a bunch of different wavefronts, if there is a reflected component of that wave, it's going to start to cause interference with the wave coming towards it. And depending on which way it's being inverted, it could cause destructive interference, or it could cause constructive interference. So when you go through different examples of these ideas where two wavefronts are coming at each other but opposite amplitudes, you got to consider the idea that they may destruct or they may invert if they're hitting a wall. And of course, if the waves are set at just the right frequency, it's going to create this idea of a standing wave. Again, I'm sure everybody here has dealt with the spring Slinky lab before, so they've definitely experienced what it means to create a standing wave. Now, one of the cool features about standing waves is this idea of resonance. And I'm going to show you an example of resonance, but resonance by definition is the tendency of an object to vibrate at its maximum amplitude at certain frequencies. So again, if we go back to the crystal glass demonstration, we hit just the right frequency so that all the glass wanted to do was vibrate at a maximum amplitude, and eventually the actual material itself can't hold shape and it explodes. Well, here's an example from the 1940s. There's a Tacoma bridge, and some of you may have seen it before. We'll just take a look, and here's a great example of resonance.
Dawn of a fatal day, and the wind begins to speak with a roar that no man can fail to hear.
And this is a
In
real
a
bridge.
40-mile-an-hour gale, the center span weaves like a ribbon in a swinging twist that you wouldn't believe possible unless you could see it as you do now. There's an automobile caught on the heaving roadway. The 11,000-ton center span twists and strains the giant cables that support it. Cables of 6,300 wire strands, each 17 inches thick.
And I'm sure you can guess what came next. Here's another example here where there's a couple kids, well, 3 kids actually, jumping on a very rickety old wood bridge. Let's see what happens when they do that.
Well-timed forces create large oscillations.
It's a standing wave. You're at resonance because they're reaching your max amplitude. In this case, though, they can exert enough force to break the object. So, you've seen definitions of constructive and destructive interference. You've taken a look at some points called nodes and antinodes. I highly recommend that if you haven't seen it yet, I would go take a look at a video or a demonstration of a Rubens tube to really take a look at the visualization of music and this idea of all these different properties. So that should be enough for you to get some work done. Good luck, guys, and we will see you again.